Now we discuss the algorithm for computing the rate distortion function. We will introduce an alternative description of the RD curve. Assume that R of 0 is greater than 0, so that RD is strictly decreasing for D between 0 and D max. Since RD is convex, for any S taking a non-positive value, there exists a point on the RD curve for D between 0 and D max such that the slope of a tangent to the RD curve at that point is equal to S. Denote this point on the RD curve by ds RD of S, which is not necessarily unique. Then it can easily be seen that this tangent intersects with the y-axis at RD of S minus SD of S. Now we write Ixx hat and the expectation of dXx hat as IPQ and DPQ respectively, where P is the distribution for the source variable x and Q is the transition matrix from alphabet x to alphabet x hat defining the random variable x hat. For any transition matrix Q, the pair DPQ IPQ is a point in the rate distortion region, and the line with slope S passing through this point intersects the y-axis at IPQ minus SDPQ. It is then evident that RDS minus SDS, that is, the y-intercept of the red tangent, is equal to the minimum of IPQ minus SDPQ, the y-intercept of the blue line, over all Q. If for a particular value of S, we can determine RDS minus SDS, the y-intercept, then the tangents can be determined. By varying over all S less than or equal to 0, we can then trace out the whole rate distortion curve RD. Lemma 9.3 is very similar to Lemma 9.1 for the channel capacity. Let Px times Q hat given x be a given joint distribution on x times x hat such that Q is strictly positive, and let T be any distribution on x hat such that T is strictly positive. Here, Px and Qx hat given x, which are given, are highlighted in blue. Then the minimum over all T strictly positive, summation x hat, Px Qx hat given x log Qx hat given x divided by Tx hat, is attained by T star of x hat equals summation x Px times Qx hat given x. That is, the minimizing T is the one that corresponds to the input distribution P and the transition matrix Q. The proof of this lemma is very similar to the proof of lemma 9.1, so the details are omitted here. Note that T star is strictly positive because Q is strictly positive, so it suffices to minimize over all T strictly positive instead of all T. The minimum of this double summation is actually equal to IPQ. The mutual information between the input and the output of a channel, with P being the input distribution and Q being the transition matrix. We now obtain an expression for RDS minus SDS, which we have seen is equal to the minimum of IPQ minus SDPQ over all Q. Since IPQ and DPQ are continuous in Q, the minimum over all Q can be replaced by the infimum over all Q strictly positive. The argument is exactly the same as the one we used in Theorem 9.2. So, we replace minimum overall Q by infimum overall Q strictly positive. Note that dpq, the expected distortion between x and x hat induced by p and q, is equal to summation x hat px times qx hat given x times dxx hat. Then R ds minus S ds is equal to the infimum of IPQ minus S dpq over all Q strictly positive, where IPQ by lemma 9.3 is equal to the minimum of a double summation, and dpq from step 2 is equal to this double summation. Now observe that this double summation does not depend on t, so we can move the minimum over all t strictly positive outside the square bracket. This will be the expression for R ds minus S ds that we will be working on for the minimization algorithm. We now discuss the Bleichert-Arimoto algorithm for computing R ds minus S ds. Recall the double infimum in section 9.1, inf over u1 in A1, inf over u2 in A2, f of u1 and u2, where AI is a convex subset of the Euclidean space of dimension ni for I equals 1 and 2. F, a function from A1 times A2 to R, is bounded from below and is such that f is continuous and has continuous partial derivatives on A1 times A2. For all u2 in A2, there exists a unique u1 in A1 that minimizes the value of f. And for all u1 in A1, there exists a unique u2 in A2 that minimizes the value of f. We now cast the computation of R ds minus S ds into this optimization problem. We let fqt be summation x hat px times qx hat given x log qx hat given x divided by tx hat minus s summation x hat px times qx hat given x dxx hat, where q plays the role of u1 and t plays the role of u2. Let A1 be the set of all transition matrix Q such that qx hat given x is strictly positive and summation x hat qx hat given x is equal to 1 for all x, where A1 is a subset of the Euclidean space of dimension equal to the size of alphabet x times the size of alphabet x hat. And let A2 be the set of all t such that t of x hat is strictly positive. We now verify that with this choice of f, A1, and A2, the requirements in the double infimum problem are satisfied. First, it is easy to verify that both A1 and A2 are convex. The function f is bounded from below. To see that, we first note that this double summation, which is an expected distortion, is always non-negative. The first double summation in f is minimized when t is equal to t star, and for that case, the double summation is equal to IPQ, a mutual information which is always non-negative. Because s is less than or equal to 0, minus s is greater than or equal to 0. And so, the function f is always non-negative and hence lower bounded by 0. In fqt, since q is in A1 and t is in A2, qx hat given x is greater than 0 and tx hat is greater than 0 for all x and x hat in the double summation. Therefore, f is continuous and has continuous partial derivatives on a equals a1 times a2. It remains to verify that f has a unique minimum when one of the components is fixed. We will deal with that later. Therefore, the double infimum now becomes inf q in A1, inf t in A2, f of q and t, where f of q and t is given as the double summation in step 1. The infimum over all t in A2 is in fact a minimum, which is equal to IPQ, and f star, the value of this double infimum, is equal to R ds minus S ds. We now fill in the algorithm details. By lemma 9.3, for any given q in A1, the unique t in A2 that minimizes f is given by t star of x hat equals summation x px times q x hat given x. By the Lagrange multipliers, it can be shown that for a given t in A2, the transition matrix Q that minimizes f is given by q x hat given x equals t x hat e to the power s times dx x hat divided by a normalization constant. The details are left as an exercise. Evidently, q x hat given x is strictly positive because t x hat is strictly positive, and so q is in A1. Let Q0 be an arbitrarily chosen strictly positive transition matrix in A1. 0 in A2 can be determined accordingly. This forms the pair Q0T0. Then compute Q1 T1, Q2 T2, so on and so forth by applying equation 2 and equation 1 alternately. It will be shown in section 9.3 that f sub k converges to f star, which is equal to R ds minus S ds.